What's up, everybody? Welcome back to the channel. So today we're going to be doing a live event, which is something a little bit different. We're going to be covering two different topics. One that was submitted via our comment section on YouTube, and then the other one is actually a project that we're working on for a client. So it's kind of like a cool demo of kind of this type of work that we do, kind of something simple, but there'll be videos out later this week, well, not later this week, but next week on each of these topics. Over the next couple of weeks, we'll probably edit this down and have a more concise answer for some of these things. But I thought it'd be cool to kind of have a live session where you guys can ping in if you have anything specific. The channel just crossed a pretty big milestone, which is awesome. And so kind of wanted to do this live and have you guys be able to ping in if you had tangents or side projects you guys wanted to bring up. By all means, use the comment section and ask away, and we'll get those addressed and take a look at them. Yeah, but so today, two main things that we're going to be going over. The first one is gears within SolidWorks. So one of the, I'll show you guys the question here. So this was the question that was submitted just today. So in your experience, without having to draw up a gear, is there a reliable source of files for gears? McMaster car models are pretty out of spec, which is true, right? So anytime you download, especially something as precise as a gear, you definitely want to be comparing the model that you get off the internet to whatever the specification is. And in the case of gears, it can be pretty complex geometry, right? So you definitely want to, if you're using the gear model for some reason where it needs to be perfect, you definitely need to compare the models to what the spec should or says it should be, right? And this kind of that caveat of does the model need to be correct kind of brings up my first point on this. So my first point in responding to this is, do you really need your geometry to be correct, right? It's kind of like using a screw perhaps, or some other piece of hardware, right? Sometimes you can have something in your model that is a dummy piece of geometry that just represents the screw, and then you know what the spec is of that screw, and it can save you processing time, especially in big assemblies where you're not trying to process those threads, right? Because that's kind of complex geometry and it takes time. And then you have a whole bunch of screws in your assembly, and that can kind of slow you down. So the real question is, do you need that geometry to be accurate in CAD or in your model, right? And one situation where I think that this is necessary, or that you would need accurate CAD modeling, is if you're going to be manufacturing it yourself, right? So either you need accurate geometry so that maybe you can create QC documentation, or another example would be if you're going to be manufacturing this maybe additively, right? So maybe you're using a 3D printer, and that's something that I've specifically done in the past on previous projects, right? We 3D printed a gearbox, and we needed accurate gears that would mesh together and function as the gearbox intended, in order to see how things like worked out, basically, right? And funny enough, actually, the gears themselves, the additive ones, what we had them SLA printed, right? Because we needed higher accuracy than what FDM would have allowed us for. But yeah, we had SLA gears printed, and they worked great, actually. They meshed together fine, and they ran well. And we were able to use some of those gears in a production environment too, actually, which is kind of cool. So that's something that so this is the first thing that we'll be looking at today is gears within SolidWorks, some sources that you might be able to use to find them, and then the ideal solution in my case, which is to just create the gears yourself, because then you know that they're going to be, the geometry is going to be accurate. All right, so let's see here. Let's make sure that the live is actually working. I gotta change the heading of this to reflect everything. So everybody hang out just a second. All right, so let's take a look at something. So like I said, this is going to be the question that we're going to be covering first, right? So part of the answer is in here. If you don't need accurate models, this McMaster car, if you don't know what McMaster car is, you definitely should look it up. So we can take a look at it here. All right, so this is McMaster Car, right? It's a website, mcmaster.com. And the awesome thing, if you are a mechanical engineer for McMaster Car, is that if you were to go into pretty much everything that they carry, you can drill down and you can find CAD for it. It is readily available and most of the time is very accurate. Now, as what's his name here? As Hyperactive Snail mentioned, the CAD for everything is not perfect. And on really critical things, like if you're doing screw threads, if you're doing gears or something like that, it is very important to check and make sure that if you need that geometry to be perfect, that you double check it yourself. So like I said, this is McMaster Car, and as Hyperactive Snail has said, the specifications for gears on McMaster Car are, or the models for gears on McMaster Car are not necessarily perfect all the time, and sometimes they can be quite a bit off. So alternatives to McMaster is, and this is probably my number one recommendation, I guess, is if you need accurate models, contact the manufacturer of your gear. If you're not making it yourself, if you're not 3D printing it, contact whoever is going to make it, like find your manufacturer, because you're probably designing to their spec anyways, right? So contact them if you need proper geometry and ask for a model. Likely they'll give it to you. So one manufacturer that I've worked with before is it KHK Gears? I believe, yeah, here you go, KHK Gears. So you can go on this KHK Gears and you can download 3D CAD drawings. Now this is metric gears. I'm not sure if they have their inch sizes available. Yeah, no, it just sends you to the PDF. So if you're using metric gears, then in that case, you can go and you can get geometry. Once again, though, you're downloading geometry off the internet, you should be checking it to your own standards and making sure it's accurate. Okay, so that brings up the final solution and the one that I've used in the past in this situation, and that is to model it yourself, right? Gear geometry is pretty standard. So there should be, it shouldn't be a problem to, let's see here, do this. It shouldn't be a problem to draw the thing yourself. All right, so let's take a look at this here. All right, so this is what I've done in the past, right? Now, this is a very old model. This is like, I don't know, probably 5 years old or so. I may not have drawn it the same way today as I did then. And there's a lot of equation work over here, right? We'll get to that in a minute. But this is what we did, or this is what I did, right? So this is when I needed to 3D print gears, because we were doing a gear train, and we just wanted to have gears in-house to test. And then we were also trying to evaluate the life of the additively manufactured gears, 3D printed gears, to see if they would be sustainable long-term in that application. We drew it ourselves, right? And so this is what we did. So I started this model. It looks like this is probably the pitch diameter, maybe? Nope, it's just the outside diameter. Okay. Which has got to be equation driven, right? Yeah, okay, cool. So this is how I built this. We'll just kind of walk through it, right? We have an extrusion, right, of the outside diameter, right? And that's probably going to be extruded for the whatever the gear teeth width is. And then we go in and we do this funky cut thing, right? And this is really the kicker when it comes to drawing a gear accurately in SolidWorks, right? There's really only one, I don't know, one part of it that's tricky. And I would say that it's this part right here. So this is an equation driven curve defined within the sketch. And these are the equations down here. You can look at them. But this is the equation that defines this involute curve, right? And so there's lots of tutorials online on specifically how to draw gears, either the geometry itself or gears within SolidWorks. Other people have done tutorials. If you guys want me to do one, I'm happy to do it. But it's kind of a standard thing. If you Google it, you'll find it. But yeah, so you can get these, you can get the equation of this here. And then this is that profile of a gear, which is usually the part that most people mess up or don't include. And so once we do this little cutout, right, then all we have to do, we fill at the bottom, we mirror it across, and then we just pattern it around, right? And so this is, this allows me to do helixes. So basically what it's doing is it's taking the pattern. You can see we're just converting this face here, right? And like I said, this may not be the most efficient way to do this, but it was a long time ago and you get better every day. So, so that's just copying the final profile and then sweeping it along a curve that is the width that we want. And then while we sweep, we use this setup here. So follow path, specify the twist value, revolutions, and then direction. And then this is being calculated within the equations based on what the helix angle is. So basically what I would recommend is build one of these files, right? You can see here that I have it labeled as a template. And that's because once you build this gear template model, all you have to do, if you build it the right way, is when you need a new gear, you just go in here and you change the values, right? Like there's really only, yeah, these five values are the only things that I have to punch in to generate any gear ever. And I know that the geometry is going to be correct, right? So that's probably my go-to recommendation. If you know that the geometry needs to be correct and you can't get it directly from the manufacturer, I would just build one of these models yourself and build it so that it's parametric and you can just punch stuff in. And what I would do is I would punch in a gear, and then you can either save it as a configuration if you wanted to like start building a library of commonly used gears that you have. Or what you could do is you can just save it out as a new part file, right? And so you just save it out as a new part file, import it whenever you need to, and do it that way. So again, here's the equations that I use to set everything up. And if you guys want me to walk through how this is built in more detail, we can, just let me know. But that would be my solution. So number one, or the solutions, the short and sweet answer, I guess, after the 20 minutes we've been here, is number one, ask yourself if you really need the geometry to be correct. If you're not manufacturing the geometry, probably doesn't need to be. You can probably get away with just a cylinder and just specifying it in future documents or however you want to do it. The second way to do it is contract with the manufacturer, because they'll be able to supply correct geometry, or they should be able to. They're making it, so they'll probably have it be accurate. And number three is build one of these template gears that's parametric, and just go in and type in the information and get it out that way. So that would be my recommendation and answer for that. So I hope that's helpful. If it is, please leave a like and subscribe, help support the channel, make sure we can do more of these videos. Like I said, we crossed a pretty major milestone. We're now able to turn on like the, I guess, play commercial stuff. We're going to leave it off for now because, I mean, we just enjoy making the videos. So yeah, thank you guys for the support on that for sure. Yeah, if this is helpful, definitely support us and enjoy, I guess. All right, so moving on to the second thing of the day. Let's see here. Let me check really quick. All right, second thing of the day is we're going to be doing a hinge design. So we have a project where we need hinges. When you open a file and don't think you've changed anything, but it still asks you to, do you want to save when you go to close it? That's, you never know. All right, so what we're going to do is we're going to do the reverse engineering on a hinge. So like pretty much everything we do, this is a hinge, by the way, right? Just a linkage, right? And this is what we have to make. So we're going to, like I said, pretty much everything that we do, we're going to start in an assembly because we have more than one piece. And we're going to insert a new component. And we're going to model this today using the top-down skeleton sketching techniques that we've talked about on previous videos. But this will kind of show you guys an application of, or like a direct application of that technique and kind of a refresher and whatnot. All right, so just looking at the part, I want to do just based on the function of it, right? All of my functionality, or a lot of the more complex functionality, is probably going to be what we put in the first sketch. So we're going to start with a sketch on the side plane, or side face. What is this called? Yeah, on the right plane. There we go. Side. Anyways, I swear I do this a lot. So anyway, so we're going to start and just looking at the geometry really quick. All right, so we basically have, we're going to make this go like this, I think. Right, so this is like the very basics of our linkage. Now there's one of two ways we can do this, right? We can, just as an example to show the motion of it, we can just reverse engineer what's here, which is probably, I mean, which would be good enough, or we can make sure, well, let me take that back. There's not two ways to do it. There's one way to do it, and that's the right way to do it. The right way to do this, you can see here, we have this motion, right, over two linkages. So what we're going to do is we're going to measure what we have, right? And then we're also going to understand that what we're measuring probably will not be perfect. And there's obviously tolerance within each of these hinges. And so our hinge sample is not perfect. So what we're going to do is we're going to measure, and then we're going to adjust the model to be what we think was the intended perfect design. And then that should be, that would be what we would want to manufacture going forward if we were to go to production on this. So we can take some measurements to at least get in the ballpark. I'm probably going to take these off of here. All right, so I'm just using a caliper, all right, to try and go center to center on the pivot points. Again, I'm measuring things like when I make a measurement, the measurement itself is not going to be perfect. So I'm trying to pick whole numbers that kind of fall close to what I'm seeing. And then we can adjust from there. All right, so we're going to start laying in the bracket here, and mostly we're putting in this bracket because it's going to help us locate things, locate these two pivot points to each other, because we have a distance between them, excuse me, but we don't know what angle they're necessarily at to ground. So we're going to start laying that in, and the square bracket is going to allow us to take measurements off of them. Also start laying in things like our material thickness for the sheet metal. So this is 197, and I know it's aluminum. So we need to figure out what gauge of aluminum is 197. So again, maybe to tie it into what we did previously, we can go to McMaster, right? And the other advantage of McMaster is that they have pretty good search functionality. So keeping in mind that this seems like it's got some type of coating on it. So the stock sheet metal thickness is going to be some thinner than what we're actually measuring. Looks like 190 is a standard. Or 5 millimeters. Yeah. So it could be 5 millimeters or it could be 190. So let's go with the 197 at 5 millimeters and go from there. All right, let's see here. The center point for these has a washer around it. That looks like they are 1/2 inch. So are you going to use that as a basis to measure off of? Now I could drill this apart if I wanted to be more accurate and model each piece and do it that way, but we're going to try to do non-destructive stuff first. So cool little trick here, right? If I'm measuring from this edge here to the washer, right? If I hold the shift key, it'll actually give me the in-between from the washer edge to the line, as opposed to like clicking on the circle where it goes to the center. So it's just a little bit faster. Now we're just going to make sure that this is centered over everything. So we're going to take this point here and this point here, and this And instead of doing dimensions, we're going to use relationships. So now we know that those two holes will be centered on the block no matter where they go. So something like that. All right. So now we need the length down here. There we go. All right, so now we have some motion, but it doesn't quite look right. So now we kind of look at the intended design, right? Another way that we could do this that might be an interesting, like, just aside, is if we weren't designing this off of a pre-existing part, right? Well, first let's put this in here. So this is the bracket that mounts to the other end, right? We're making, oh, hey, we're making a bracket, or not a bracket, a hinge. So this is a 4-bar linkage hinge, so that when we, I can show you here. So that as the door opens, it actually moves in space, right? As opposed to just pivoting around like a normal hinge. Again, we're going to use that same trick of measuring off the washers to avoid doing destructive tests or destructuring of the sample. Also keep in mind that we're measuring off of sheet metal, something that's been formed, right? So not everything's perfectly squared. Like even some of the edges on this have burrs or bumps or different abnormalities, I guess would be the phrase. So the measurements themselves aren't going to be 100% either. So we'll have to go back and model it the way that it was intended, not just the way that we see it, and just blindly throw numbers in there. All right, so if we bring this down here, yeah, we have a relationship that we don't necessarily want hidden somewhere in our relationships. So if I freeze this, I don't know, maybe not everything. No, I think it's, we might be right. Let's check and see how close we were on that. Yeah, okay. So that's probably right. All right, so now we have our bracket on the other end of the linkage. Okay, so Stoic stimulation is asking how should I go about learning how to make models that are easily adjustable in SolidWorks. Good question. So the best thing that I would recommend, I guess, is to just practice modeling things, and more specifically model something that's useful to you, and think about how it would be changed in the future, right? So if you think you're going to model something that's injection molded, right? Maybe you want to make draft flexible in it. Or if you're like going back to, so at the beginning of the live session, we did helical gears, right? And in there, I have a model that's a template for me. So basically, if I need any helical gear shape done, I can go in, punch in the specifications, and that model will generate what we want. So that might be a good like example. Basically, you just need, I mean, how do you get better at it? I think the best way to do it the best way to learn it is to do it. You have to find problems that you need to solve, and then in solving those problems you get better at it. If you have like a specific example of something that you're trying to do, we can take a look at that if you want. That might be a good idea, but just in general, I mean, you got to do the practice of trying to make something adjustable in some way. I mean, as far as like topics to look into, parametric modeling obviously is like the base function of SolidWorks. I'll make the cascade elevator with an easily adjustable height and width. Okay, so in that case, if it's an assembly and you're just changing your sizes and then you want everything to like auto update from there, watch my video on, well, we're kind of doing it right now, but watch the video on skeleton sketch modeling. Yeah, if you're trying to make a model and you want it to change based on just changing a few dimensions, skeleton sketch modeling, especially if it's an assembly, right, where you have more than one part and you have to pass those relationships against each other, watch our video on skeleton sketch, like top-down modeling, because that's the best way to do it. So there's two different modeling methodologies. There's bottom-up, which is where you, let's do a FaceTime real quick. So there's two different methodologies when it comes to parametric modeling. There's bottom up, where say I'm drawing a block with a hole and then a pin that goes through it, right? Bottom up is where I model the block and I define the dimension, and then I model the pin and I define the diameter dimension, and the two diameter dimensions that I defined go to get like match, right? So top down is where you create some type of relationship, basically, or variable defining what that diameter is, and then you push it to the two parts, right? And that's really what skeleton sketch modeling does. It allows you to create a sketch that can be used by multiple parts, and therefore they're all sharing the same information that's in that sketch. And so when you change the hole diameter, both parts update, right? Like changing the hole diameter is changing the pin diameter, and therefore both parts match. And so that's really what you want to do, is you want to look into methods of doing that that allow you to push information to multiple parts. And to me, the skeleton sketch method, or like this method that I'm working on right now, that's the most efficient way to do it. And it seems really robust within SolidWorks. You can make a lot of changes very quickly for me, and two, my tree doesn't crash all the time, right? I'm not changing one thing in one part and it causes this cascade failure of features across a bunch of different parts. And that's the other, that robustness is an important piece. Another side, like, I don't know, another side piece of advice would be, don't try to use dimensions to control things. Try to use relationships to control things. So like going back into this sketch here. Let's see here. So going back into the sketch, right? I have a bunch of dimensions here. But if I were, but I, like, for example, right? I have a bunch of dimensions, but I only dimensioned that this diameter once, and then I used equals everywhere else, right? Same with the trick of doing this as symmetry, right? Like, I know what the width of this is, and I know I want these to be symmetric across the width of this bracket, right? Like, we want these holes to be, you know, centered across this bracket. So I could have, you know, done a dimension here and then a dimension to the hole, and then, like, you know, used math to figure this out. But this symmetric dimension will keep the relationship no matter what size I make this. And it'll do it, to me, it's more efficient and more robust. Like, it's less likely to fail, because sometimes you'll get in a situation where the solve order in SolidWorks will mess you up, right? And you have to hit rebuild to get your parts to solve properly. And so the sketch relations seem to be a lot more robust by reducing those errors, rather than using like dimensions to define everything. So yeah, I think that would be my two biggest like pieces of advice. Now that I've rambled for a couple of seconds and had some time to think. One, look at top-down methodologies, specifically skeleton sketching. We have a video on that. There's also a really good PDF out there on the interweb somewhere that somebody did up. And then number two is try to reduce the number of dimensions you have in any one sketch as much as possible. I think those are probably the two biggest things. Like, try and use relationships to define things. And also, I mean, third caveat, I guess, or third would probably be to use like the pattern tools. So symmetric, linear patterns, curve-driven patterns, rotational patterns. Like, never draw something twice that you can draw once and then pattern, right? It'll just make everything, one, that your models will solve a lot faster, and two, it'll like save you from having to do the work, and three, any change that you make to that core, to the core of the pattern, will then be propagated, and so it'll reduce errors as well. So yeah, I think that's like, as far as how do I make things adjustable, one, top-down modeling, two, try to use dimensions as sparingly as possible, try to use relationships when you can, and three, use the patterning tools. That would probably be like the core class of how to do parametric well. I hope that helps. If you got any more questions, feel free to put them in the chat. All right, LB Green says, what would be the best process to create an automated hinge system for an automatic deployment? I guess it kind of depends on what you mean by automated hinge system. If that sounds like more of a design question than a SolidWorks question. So it would depend a lot on like what the application is, you know. I mean, if you're trying to do automatic deployment of a hinge, like, do you want it to be powered by, you know, electric motor? Do you want it to be pneumatic? Do you want it to be, there's a bunch of different solutions there, I guess. Oh, landing legs on a spacecraft? Oh man. Aerospace. You know what? I don't know, LB Green. That would be the short answer. There's so much that would have to go into trying to determine like what you're landing on. You know, obviously weight becomes the issue and factors of safety, right? So you're, as far as like designing, you're obviously doing a lot of optimization there using simulation and whatnot and testing before you go. Welcome to SolidWorks from Fusion 360. I have not used Fusion 360, but hopefully SolidWorks is being kind to you. I mean, I know that it's another parametric modeling software. So depending on what your experience is in Fusion 360, like a revolve is a revolve, right? You're either cutting or adding material. I mean, it's really just learning that type of stuff. To me, the stuff that sets SolidWorks apart is the intricacies of like how do you go about structuring models. And to me, is probably the biggest reason that I stay within SolidWorks and don't go move to something like Onshape or Fusion 360, is that I have the experience in building models within SolidWorks to be really stable, and the learning curve there hasn't pushed me out yet to make a change. Yeah, I would say as far as is Fusion 360 similar to SolidWorks, I would say they're very similar on the basis of they're both parametric modeling software where you're using different features or commands or whatever you call it to manipulate sketches to create geometry. There's intricacies within each program, I'm sure, but that's like the main gist of it. They're very similar. So as far as equations, going back to the parametric modeling, the equations side of it, equations, you can think of equations here. We'll go back and hold on one second here. So we'll go back and we'll look at the helix gear, right? All right, so this helix gear, right? This is a template part that I did many years ago when we were planning to 3D print helical gears, or just spur gears in general, really. And we needed to make sure that the geometry was correct. And at the time, we were also looking at doing like a custom gear design, whatnot. So as far as like the equations, so within SolidWorks, equations basically are just a way of creating variables and then manipulating those variables inside of equations, basically, to create other variables, really. So like if you look at the way that I built this gear part, I've got basically 5 variables that are user entered, right? And then every other variable in here, these global variables, every other variable in here is just a manipulation of these original 5. So I can punch in these 5 pieces of information and generate any gear profile that I could think of, really, like that exists off the market or on the market or off the market. And so that's the power of variables, right? And then you can get another level even past variables and look at design tables, which is basically taking these variables and expanding it into configurations, right? So you can look up design tables. That might be another thing to look into. But basically it takes each variable and makes that a row, and then you have columns, and each column is a configuration. And so you can just punch in mass amounts of configurations, basically, that's sitting there manipulating those 5 parameters, and I can generate. That's basically what McMaster-Carr does, or any company that's creating a large library of different sizes or parts, right? Is they're taking a really well designed base model, and then they're manipulating a few variables, and they're just making configurations in every size and shape that they need. And so that's how you would do that. I hope that's helpful. Yeah, you guys are very welcome for your answers, for sure. Okay, great question. I'm still learning how to make a multi-body component in the same project. What's your opinion? How is it easier to do those and make each part separate and then assemble, or should I make it in the same? I 100%. Yes, jumping down to your next question of can you use variables within the design? Absolutely, that's literally what you're making them for. So in equations, right, you name your variable and then you put in your answer. Say we wanted to put a hole in here, right? So sketch, right, we just do this. You can make the, when you go to dimension it, right? So from here within SolidWorks, say you want to make this like variable ID, right? You'll see how this is coming up and it's going to prompt me now. Do you want to make a new global variable named ID? Yes. And I want to set it to 1/2 inch, right? And then I want to extrude cut this through all. Actually, better do through all both. And now I can go into manage equations and I have that 1/2 inch right here, right? Okay, I didn't make it 1/2 inch, but say I wanted to make it like 3/8 when I kick out, because it's rebuilding the model right now as it closes. I can go in here and now it's 1/2 inch. Oh, I didn't link it, that's why. So equals, I made the variable, but then didn't link it to the dimension. So now I set it to equal ID, right? And you see it snaps in. And I can go back and change. So I can make an ID, I can make an ID times 0.5, right? So it's all in there. And then it's just equations, right? You're just saving information and able to reuse it later, and that is huge when it comes to. I mean, it's very valuable when it comes to certain types of design problems, right? When you're generating a mass amount of sizes or shapes or something like that, it's a great solution for that. All right, let's see here. So going back up to whether or not you should design the parts separately. So I think this is the guy who's coming over from Fusion 360. If you're using SolidWorks, hey, I appreciate the kind words for sure. Hey, like and subscribe, right? Anyways, yeah, so going back to whether or not you should build top down or bottom up, always, if you can, build top down, in my opinion, right? You're the only time I would ever do something bottom up is if a design is locked and you're modeling something that you don't think is going to change. But even then, like, I can talk myself into doing top down anyways, right? I would always model in relationships if you can. And yeah, I guess that would be the one rare situation where you would do bottom up is if you're not designing a whole system, you're just designing one part that's going into something. Then you could like pull dimensions off of the assembly it's going into, and again, learn top down. I guess that's like, yeah, I'm trying to pick a side, but really to me, top down is the way to go. So top down is specifically within SolidWorks coming from Fusion 360. Top down is when you're going to, or the way that I like to do it, here, we can go to, let's see here. We can go back to our previous project. So we're not really done, but, or we're not very far along, but so this is going to be a bracket. We're reverse engineering this bracket, right? So it's got basically 4 major components and it's got all the hardware. But the way that I'm doing it is I'm inside of an assembly, and then I create a part, and then I create sketches within this top part. And then what we're going to eventually do, I can show you for an example. So we're going to make a new part within this assembly. So this is called the skeleton sketch technique, or whatever you want to call it. This is skeleton sketch, top-down modeling. So I've got another video on this. But basically, what we're gonna do is we're going to use a feature called derived sketch. And what derived sketch does within SolidWorks, it basically takes a sketch and copies it into another part file, right? And when we do that, we get this thing here. So this can, so you can see here that if we hide this part, because this is actually that top one, right? So this is our new one that we'd be making, right? If we hide this here, we can see that this is, we can manipulate this, but we can't change the dimensions or shape of it. So basically what it's doing is it's creating this copy of the sketch. And that what that allows us to do is, now imagine we design 4 different parts, right? If we copy that same sketch into those 4 different parts, we're now passing information amongst those 4 parts at the same time. So if I go and I change this linkage length, all 4 parts will update in turn. And so that's top-down modeling, right? I make a change at one location, and that information is pushed down the tree into the other parts, and everything else updates. And so you're no longer making these linkages or these parts like one thing at a time, and then you change one, and now something else has to be updated, and you're missing all, like, that's where it gets bad, is you go to make a change, and if that change isn't propagated correctly by you manually in bottom up, you end up with errors, right? Like you go to put your pieces together and they don't go together because one part in the chain missed the update. With this, we're literally creating that chain as we go, and so we know that when we make a change at the top, it's going to trickle down. And so that kind of also goes back to the question of how do you design to be flexible. It's techniques like this that push the information down to the parts, while still maintaining the relationships. So I don't do regularly scheduled things. It depends a lot on, well, I'm trying to put out like a video a week, and I'm failing at that. But I don't usually do a preset time or anything like that. As far as scheduled, if you want to watch the live stream, one on YouTube, I'm pretty sure you can just go to the bottom as if it was a regular video and just drag back to the beginning and watch from the beginning. And when I close out of here in the next 5 minutes or so, because it's the end of my day, when I close out of here, it should post this to our account as a regular video. So if you wanted to go in there and watch from the beginning, it'll be posted as a regular video as well. You have to get through a bunch of my rambling and stuff like that to find what you need. But hopefully we can take these videos and chop them up into so hopefully we can take these live streams and chop them up into individual videos. So master model is another way of doing top-down modeling. I don't use it personally, but that's not to say that it's bad. I think that, so my understanding of master modeling is that you're inserting a part file into other part files basically as a reference. And to me, I think the inserting just the sketches seems more stable to me, I guess. I don't know. But it seemed, I have wanted to do a comparison on some project where I basically take the same project and model it to like using skeleton sketch and master model, and seeing which one's faster and more robust. I just don't have the time to do a project that would be big enough like that to like analyze the two, I guess. But I know of master modeling, but haven't used it extensively. To me, I know that this derived sketch stuff works and it's really stable. I used to design top down, where I would click on edges and stuff like that and convert entities into the parts, and that works, but it's just not as stable, right? Features break as you keep doing more and more stuff. And I know that master modeling is one way of eliminating that. I just am not familiar enough with it to say you should use one over the other. All right, so the question is, my point on assemblies, let me give an example. What if you want to make a bolt and a nut with some clearance between them for 3D printing? What are my opinions on the approach? If you want to send me that file to compare to skeleton sketching, I will be happy to take a look at that, actually. So info@forgepd is our Gmail, or is our Gmail, geez, is our email. info@forgepd.com. So send your, if you want to send that sample file to us, I'm happy to open it and I'll take a look for you. And maybe that might be a video where I can just copy that file and redo it with skeleton sketching. I will try to, if live sessions are really helpful for you guys, which it seems like it is, to be able to just ask your questions and get your answers and whatnot. And I kind of like this, like, reply and I mean, it's more fun for me, right? Because before you guys started talking, I'm just sitting here modeling something. It's kind of boring to watch anyways. But yeah, if the live stuff is preferable, maybe we'll do a live session like once a month or once every couple weeks and do something like that. All right, so really quick before I go, let's take a look at, let's see here. Let's take a look at how I would do like a nut and bolt, or what was the example? A bolt and a nut with some clearance in between. Okay, so let's just, for example, right, say we're going to do that. So we have in skeleton sketching, say we're going to make, say this is our block, right? Right? And we have this very simple sketch, right? And now we need to make a pin. So we're going to go here, we're going to go new part. And we're going to do the same thing. Now we want to make sure that we're pulling the derived sketch from the correct location. So what we're going to do is we're going to isolate this top part. One thing with SolidWorks, you always want to solve down the tree, right? Which is actually part of the reason why we're not just making our sketches within the assembly. We're actually making a part file to hold our sketches. There's other advantages of that as well, but you want to solve down the tree in SolidWorks. And so this part is holding our sketches. Therefore, when SolidWorks hits this, it's going to solve this part, which includes our sketches, and then it's going to push it to the rest of the tree. Anyways, side tangent. So we're going to do another derived sketch, right? So we can hide this. And we're just going to fix this in place. All right, so we have the same sketch in both parts now, right? We have our block, and now we'll just do our pin. and say we'll make it 3, right? And so the question becomes, how do you account for the gap, right? Because we have, we'll hide this sketch here. Because technically we imported the same sketch, but we don't have a gap, right? So there's 2 different ways you can do it. And my jury's out on which one is best. And it kind of depends on the situation. The first way to do it is pretty simple. You simply draw in geometry in your original sketch that has the gap, right? Hold on. All right. So like I was saying, so the simple or one solution would be you simply add sketch geometry that controls your gap, right? So now we can make a relationship between the hole and our pin diameter, and we can say, all right, we want the gap to be 50 thousandths, right? Because we're going to 3D print it. So now when you go and you design your pin, you simply pull the geometry. Instead of using that circle, use this circle, right? So now just as an example, so now we have a 50 thousandths gap between our block and our pin, right? 50 thousandths. So now, just as an example, right, we can go in here and say the factory comes back and says, hey, that diameter should actually be 3/8, not a 1/2 inch, right? We change one number, this changes, our gap stays 50 thousandths. We exit here and all this is pushed to our other parts. So now we have a hole that's 3/8 and we still maintain our gap, right? That's 1/2 inch. Minimum distance, 50 thousandths, right? So that's one way to do it, right? The second way of doing it, now I would recommend, I do like that way of doing it when your sketches don't get too busy, right? If you have a lot of geometry in a sketch, which is easy to do with skeleton sketching, like even I have to consciously say, okay, what do I really need to put in this sketch, right? So if you can keep your sketches simpler, that's better, right? You're spreading that sketch file over a bunch of different parts, so the more lightweight it is, the better. So if it's a relatively simple design like this, you might model in the 2 different size of diameters. An alternative would be if you go in here and say, let me just do this. Now it's going to break because I removed the geometry that we were referencing, but that's okay. Because in this example, you would just do the original diameter. So we're going to delete this, and instead we're using this diameter here, right, which is the same one as the hole. So what I've also done, and this has advantages and disadvantages, obviously, but you can go to surface and move face, and you're just going to offset 50 thousandths, and you flip the direction in this case, and there you go, right? Now we have the exact same geometry designed 2 different ways, and each one has its advantage. In the sketch, you're able to see the difference, which might be of value, but it makes things more difficult. In this situation, you don't see it within the sketch that there is a gap, but what I sometimes like doing is I'll model everything line to line, and then I'll go back in and do where I know there's going to be gaps, because you can use interference detection. Where is it? You can use this here, this interference detection to detect where two parts touch. And then I can go through my tree with interference detection turned on and go and prescribe those gaps and move those faces in as I go down to release a design, right? So that's kind of a good check and good workflow that I found. Like, okay, I know I want, maybe I want a press fit, or maybe I'm going from a slip fit to a press fit, and I don't want to have to change the sketch that's there. Or I want to try and keep my sketch lightweight or something like that. Because usually the points that contact on a part are, like, for example, on this, right? We've got this whole block, nothing touches. The only thing that touches are these two surfaces. So I only need one move face command in there. And then also you can relabel your move face as, like, I'll rename it as gap 1, or, pin gap or something like that, or pin tolerance or something, so that I can search within my tree and find it very easily and look at all of my gaps and make sure that my clearances are the way that I want. So anyways, yeah, that's two different ways of doing it. So the same thing when I have threads. So your threads, I would do this way, because it's going to be easy to draw the threads in and then just simply offset them a little bit. And you can offset on both sides, right? You don't have to do it just on the pin. I could have done 25 thousandths here and then go to the hole and move face and do 25 thousandths. And then if you're really getting smart, you put the gap as a variable, and then you push that variable to the individual parts, so each one is always offsetting the same amount. So you want to keep the 1/2" pin, but make the hole larger. Yeah, in that case, it depends on how you drew it, right? And in the case where, and maybe this is another good point to bring up, right? A lot of how you design something within SolidWorks should be based on what the thing is. If I know that my pin is always going to be 1/4 inch because that's the one I'm buying from the store, right? Then I'm going to offset the gap on the hole that we're drilling, not the pin, because the pin is going to be the thing that sets it. So if we want to keep the pin 1/2 inch and make the hole larger, and you don't really care what the pin is or what the hole is, then I would do it the other way, right? I would make my hole, or I would make this sketch 1/2 inch, like keep that. But I would delete the move face here and then just put my move face here. Because now I know it really comes down to, what do you want to control? What do you think is going to be the basis of that feature? So now we're here, right? 1/2 inch flip offset. I don't know if there's enough clearance here. Yeah, it's going to go through the wall, but call it 10 thousandths, right? Make sure your direction is correct when we're doing these really small movements, because 10,000, like, which way is it actually going, right? So double check your directions if you're moving in a small amount. But it's a great way to do press fits too, right? Like, say I wanted a 10 thousandths press fit or 20 thousandths press fit. Now you just flip your direction and you have what you need. And the original sketch is much cleaner. And so that is one thing that I like about doing the gaps. I can prescribe them where I need. I can use interference detection to find them. It keeps my nominal geometry the same across parts, and then I can tolerance up or down depending on what the situation is. All right, sweet guys. I am out for the day. I hope this is useful to you guys. I still have to finish this bracket. So if you guys have questions, I'll probably be around either, I mean, maybe I'll try and do one of these guys tomorrow. If you guys have more questions to do, maybe we'll do it tomorrow. Yeah, variable suggestion, or like pushing a variable down the tree is awesome, right? Because say you have like another example that I've used in the past is draft angles, right? Say you design a part and you have a draft of 1 degree because you're thinking it's going to be smooth, and then the manufacturer comes back and says, hey, actually draft is 3 and your nominal material thickness isn't a quarter anymore, it's, you know, an eighth or something like that. I can go in and change my 1 degree draft to 3 degrees and my nominal thickness from, you know, a quarter to an eighth, whatever it was. And when I hit go, every one of my parts will update and just trickle through, and then there's no going back and, oh, did I miss something? I mean, it's awesome when you set it up the right way, and it saves you a ton of work. It's awesome. Okay, so maybe we'll do that tomorrow. Maybe we'll look at that tomorrow. Let's I don't know when I don't know when I'll be on. I'll be honest. It'll probably be tomorrow afternoon, maybe, or sometime in the morning. I'm not sure. I have to do this bracket, so it'll probably be first thing in the morning tomorrow. Let's do that. So it'll probably be like I don't know, 9 o'clock Central Time, go live. And I'll try and remember to, yeah, so we'll do a variable. We'll do passing information down in a variable, and I'll try and get like 5 minutes more of this bracket designed, and we'll go from there. All right, guys, have a good one. Please like, subscribe, do all the things, support the channel. That'd be awesome. And if you guys are engineers and you work at companies that need engineering support, that's what I do for a living. So my company is Forge Product Development, and we're basically mechanical engineering consultants. So by all means, reach out to us if there's a project we could help you guys with. You guys have a good night, and we'll see you next time.